All right, guys, we're going to get started here. So today we're going to finish up that CNN architecture. That's basically the convolutional neural network. It's like we've covered deep neural networks and how they are. And then I still need to, like I said, cover a little bit of the background of how CNNs work. But basically, they're just more complex neural network architectures. They're definitely the thing that everybody uses for images. Okay, definitely. So that's what I'm going to do today. I haven't posted this code to the GitHub yet because I've been trying to figure out there's a bug in it apparently that some students have found. So I'm trying to find it.
Do you want me to just email you the thing I use?
Yeah. So I'll tell you. So are you guys still having that issue, right? On your GPU, you instantly get higher. Yeah. So I'll talk a little bit about that, and we're gonna try to figure it out today. I honestly don't know what it is. So I have I'm gonna try something today. So I'm gonna kind of do this with you guys. So today we're all working together, right, to get this to be pretty good. Um, I already let me actually get one of these, the Jupiters, and I'll show you the script that I'll provide for all of you. So I've added everything, the checkpoints, saving procedure. I've built a very basic CNN, so I leave it to you guys to explode that and make it more powerful. But we got, okay, so here, so we are now recording and the Scholar is running. So one thing that I do recommend you do when you're saving your checkpoints is that you save them to the scratch space of Scholar, because there you should have 1 terabyte is my understanding. All right, so I'm going to do clear here. So my quota, right? So you guys know where this is, right? So you can get to this terminal. You can see I have 1 terabyte here, and I believe you all have, yeah, Henry.
By the way, I think Scratch every 3 months or so deletes.
That's fine. They'll be done.
Yeah, but you want a trick. The way I saw the way they implemented the check, they checked the last modified stamps. So if you just go through all your files, like a script or something, and run touch command each file, it'll never delete your files.
If you just touch a new one,
yeah, if you just touch the file,
like every week, just add a new one, they'll never delete the whole.
Not add a new one, but if you
touch
the file itself
that you don't want to be deleted, so they do it per file.
They do it per file, yeah.
Oh, interesting. Okay, all right, I see that.
I think.
Okay.
Thanks for Android.
All right, great. So anyway, so if you guys run my quota, you should get something like this, correct? My suggestion, and this should say 1 terabyte, possibly. Yeah, I don't know. Does it? For Scratch Scholar? Well, my understanding is you have 1 terabyte. I don't know. So what I would suggest is, what I've been doing is saving my checkpoints here, okay? So I have ls-l. This shows me so I'm in home and my user. If I want to get to that Scratch, I'll do cd / Scratch Scholar. Is it my user? Maybe. Yeah, okay. Yeah, and then you can see I was running this earlier today just to kind of try it out, and you can see I have checkpoints there. All right, so these are basically the CNN model that I'm training. Every 5 epochs, I saved a copy of it. And that way, you guys, if you want to train for 24 hours, you can just grab the last checkpoint, and keep going. Does that make sense? Yeah, everyone with me? Any questions? All right. So that's one thing, is just, dealing with the cloud, which is going to be your future probably, right? So dealing more with the cloud, we have to get used to things like this. All right. So now, yeah.
I don't think there is a limit on Scratch for us.
Oh, well,
but it says
great.
It says limit is 0 kilobytes. I just made a file of 8 kilobytes. It was in Words.
Okay.
So
Yeah, I was told I had 1 terabyte. I mean, I can see it right there. All right, so now, yeah. Okay. All right, so I've created this new script. It's similar to the one we had done before, and this is the one I will provide to you guys at the end of class today, by tomorrow at the latest. And this is what I suggest you use for the competition, okay? Make sense? All right, so it's called Checkpoints CIFAR-10 Challenge CNN. All right, so I have done simple multi-layer perceptrons. We've done deep learning models, I believe, deep learning architectures. And I am only touching on like advanced deep learning with CNNs, like only scratching the surface here. But, you know, for this challenge, you probably need a CNN. So next week, yeah.
Question. You say you're selling GitHub?
Huh? I have not posted it yet.
Oh, not yet.
Not yet, but I will post it because there's one thing I need to figure out today, and that's what we're gonna do in class. Okay? Yeah, but it's very so I'll describe the code first because it's very similar. Like 60% of it is probably what we had done before. And then I just want to point out the new things that I added, okay? And the thing that we need to add. So one funny thing that's happening apparently is that some students who have their own GPU are grabbing this exact same code, running it on their GPU, and they're getting like 0.40 F measure right away. You're also having that, Aiden?
Yeah. I didn't think it was an issue because we were at like 15, and then I was like,
you got 0.40 then?
Not doing anything.
Oh yeah, so the exact same code that I have, right? So that's very strange. So that
I think it's the environments that's the issue.
I tried different environments today, like all the different environments that I have. But anyway, let's.
Right.
I'm telling you guys so that you're aware of this issue because we need to solve it, right? We need to figure it out, and I'm sure it's not difficult. Henry, let me just finish. Yeah, and then but yeah, okay, this is where we're at. So the code works, and for some of you, immediately, if you run it on your, I have a GPU at home. I haven't tried it there, but I'll probably run it on the weekend, and I might get 0.40 as well, right? So there's something in the Scholar environment. I was thinking, I'll show you one of the things that I did that usually fixes errors, but that doesn't seem to be doing it either. So we have to think about what the issue might be. So anyway, I want to describe this code. Basically, it's very similar to what we had before. Libraries. I provided some links here just so that everything is there. So for instance, the data set is there, right? That you guys download. I provided notes on how to save the checkpoints and everything. That's there, although I provide some code sample as well. And I provided this, which is from my notes, my book on CNN. So if you want to read more about CNNs, dive in, right? So it's a blog post type of thing. Check it out. But I will describe CNNs in a very basic way. I'll give you some intuition of how they work. All right, but we'll leave that for next week, all the theory. So anyway, we got our torch functions. We've got our sklearn functions. CUDA, we can see that CUDA is an NVIDIA A30. You know, the train test set, that hasn't changed. I did add this new thing called the path to the checkpoint, and that basically is where you're going to be saving your checkpoints. Does that make sense? So that now it's a good practice. You know, your program breaks for whatever reason, or you run out of the 2 hours, you can just retrieve like one of the latest checkpoints. So currently what I'm doing is I save the model and I add the epoch. So that way I know, like, I can look at all the epochs and just say, okay, I'm going to grab not the last one, but the one before and keep going. Okay, so you can play with that. But anyway, I added this. Then this is exactly what we had done before. The train data, this has not changed at all. Just getting the images. All of this is the same. All of that is the same. So none of that has changed. None of this has changed. We had the image of the cat. We checked the balance of the data set. So all of that is the same. Then we do the same for the test set. All of that is the same, right? So we do all this, check the distribution of the test set. Well, that's the same. Now here, I did try this. So in the past, I always have converted my data to float 32. from float 64. So I thought, okay, maybe the error is some kind of a memory issue. So you can see all I did is I took the tensors, converted them to NumPy. I'm sure you can do this in Torch, but this is how I've always done it. Converted it to NumPy, changed it to float 32, converted it back to Torch. And I was hoping by doing this, it might be a memory error. I've always used float 32 for everything, but it didn't change the performance. So it's not really the solution. But it's something I did try. And actually, I always do this in all my code. So I thought maybe that would do it. All right, so then this is all, so this section is new. That's why I added this new heading, but it works. Like you can comment it out and it basically works also, okay? So then I have the printing, you know, this part's here. Creating the list is exactly the same. And then we create the data loaders, exactly the same. As far as the architectures, currently for this one, I'm not even thinking about deep learning or MLP. I'm only going to focus on that CNN architecture. I believe we had started to describe it. Remember, it's just, you have layers just like before, but these are special layers, right? You know, these, and think of them intuitively as an image that is being multiplied times another grid, another matrix, but it's a different kind of a multiplication called a convolution. That's why it can't be called a multiplication, because it isn't. You see that? It's a different kind of operation called a convolution. And the intuition is you have an image and you're running a filter through it. And once you're running that filter through it, you're converting that image into however many different versions you have, with the intuition that those filters are not created by humans, but they are in fact weights that need to be learned based on the problem. So the neural network learns like the really good filters to use. Okay, that's powerful. So anyway, remember that if we flatten the images, it is 30 by 72. A CNN does not require the flattened vector. And in theory, they're actually faster than if you run the flattened version. So there should be that advantage in terms of speed as well. All right, so just give me a second. Let me finish this. So then this is the architecture as is. And I think it's exactly the one that I did on previously. Okay, so I didn't change it because I haven't given you a super deep CNN. You can make this way deeper, right? So, but you have to add tricks to it. Like something, I'll tell you right this. If you decide to make it with 20 convolutions, first of all, it's going to take a long time. And second, you need to use a thing called residuals, okay? Which is like, you know, a thing that you would add there. If you don't use that, it's not going to work. You already knew that? All right, good. So anyway, you have to use that because otherwise, I think I've given you this example. As you multiply these values, they become smaller and smaller until they become zero, and then the neural net learns nothing. So when you use that technique of the residual between layers, it will help out a lot. But anyway, so as you can see, this is the same architecture as before. The NN sequential, one convolution here, a second convolution there. And basically, as we had discussed, you have to start by saying that you have 3 channels. Why? Because they're color images, RGB, okay? This is the number of filters, so I just did 16. The kernel size, I always go with 5 by 5, and then the strive and the padding is 1. That's basically it, okay? Then the max pooling here, the intuition is if you use it like that, it cuts the images in half, like it shrinks them from 20 by 20 to 10 by 10 and so on, okay? So it's cutting them in half. And then you want to throw in a ReLU activation in there as well, okay? But you can play with those parameters. So basically, the image comes in through here, or the batch of images comes in through here. It goes through this first convolution, and the output of that goes into this, next convolution. Notice that this parameter and this parameter need to be the same, right? Like you're saying the output 16, it's the input 16 to the next one. Now, this is the part that I didn't do the last time around. So once you are done with the 2 max pools or 10 max pools, or sorry, convolutional layer, 2 convolutional layers or 10, now you need to feed that into a feed forward. So this is actually, I want to show you this. That's why one of the reasons why I added the link. So I have this exact same architecture there in a model. Okay, so basically, only I did it for MNIST, so this is not CIFAR, but it's the same idea. Image goes in here, then you have convolutional layer 1, convolutional layer 2, and then it just ties to a fully connected layer. Do you guys see that? But this, think of this as coming out as a hypercube, right? So what do you need to do that? You need to flatten it. And once you flatten it, then it becomes a flattened thing that can connect to the next layers until you get to the output layer, which is 10. Do you guys see that? So getting that value, it requires a calculation, but it's easy, right? And that's one of the things I provided. Okay, so how do you do that? Right, let's go back to the code. So as you can see here, in my architecture, I wrote feed forward, then that hypercube that comes out of the convolutional layers goes into this flatten. As the name implies, it flattens it, right? But then it flattens it to what exactly? Do you see what I'm saying? You can see that I've already like magically added this number, 1152, right? So I added that number, but you know, what is that number? Where did I get that number? Before I had left a question mark there. So I'll show you, I have a script at the bottom of this that will show you how to compute that number, okay? After you've got that 1152, then, you know, you can decide what this is. But you usually use that funnel approach, so 512 seemed like a reasonable thing. And then ReLU, and then 512, and then 10, and then softmax. I'm going to change that to softmax. Right. So anyway, so that just basically, as we've discussed, over the 10 probabilities that come out, you make that distribution add up to 1. Okay? So that's basically all that's happening there. That's it. All right. So this is exactly what we had discussed before, but how did I get that 1152? And then we'll come back to this. So at the very bottom of this script, I always like to do this. And everything that's complicated like this at the bottom, I put in this section called figure out the dimensions of the thing. So it's a nice trick that you can do. So all you need to do is grab the class, right? Here I just grab NN sequential. It's the exact same architecture, but I cut out everything and just left it at the flatten, because what's important about this is that the vector that comes out of there is going to be the hypercube flattened, right? So once I get it out, what do? Just print shape. And then I know exactly what it comes out to. Do you see that? You guys understand what I'm doing? Yeah. All right, so that's what I'm doing here. So I'm being consistent. I use a batch of 16, and then I just took the exact same architecture until flattened. And then what do I do here? I'm going to create a fake tensor, mimicking the batch. Which batch? The XBYB, right? So if you remember when we are training the model in the training loop, we do this, right? For XBYB and train DL. And at that point, I have a batch that probably is 16 by 3 by 32 by 32. Do you guys understand? And then that thing feeds into the model, and the model gives me an output. So that is how I'm figuring out what that shape should be. So I just create a fake one. So then here, as you can see, I'm going to run this part. Hit run, 16. The layer is going to give me whatever the flattened cube is. So I'm going to hit run. Oh, I need to run all the libraries. Okay. All right, so it ran now. Let's see if that works. So in case you guys change your architectures, which you might, that number would change, right? So just copy that architecture to the bottom and run this one. So run the batch, run it until flatten. Okay, worked. Create a fake tensor. You can see it's very easy to do that. Just do torch.rand because the values in it don't matter. What matters is the shape that comes out that needs to be consistent so that the model does not break, right? That's really the key. So now what am I doing? 16 by 3 by 32 by 32. That's what a batch would look like going into the model. All right, and then what do I do once I have that batch? I feed it into model RC, which is this one over here. And this only doesn't have the feed forwards because really I need to figure out what that shape is after the flatten operation. So I'm going to do that. And there it is, my 1152. Do you guys understand? Why 16 by 1152? Because it's a batch of 16 images, right? There's 16 images in there that went in. Like one was a cat, one was a dog, one was a car. Each of those went through the convolution, and then they get flat. So that 1152 now is this one here that I add. There's other ways of figuring this out, but this is the approach. Any questions on that idea? Sense? All right. So running this, then those are the changes. Here's the training loop. If you notice in the training loop, I did a couple of things. One is I commented this out. Why? Because before, if you decide to just use the deep neural network, then you need to flatten the images. But the CNN takes them as hypercubes, right? Of 16 by 3 by 32 by 32. So you can just comment this out and everything else works. Got it? Okay. Now here, notice I also added a little bit of code. So before every 5 epochs, I was printing the loss. But now also I decided to save the checkpoint. Okay, this is where I save it. So how do I save a checkpoint? I already have the path. What is the path? Scratch, right? The scratch path on Scholar. And I wanted to have several, so I just appended the epoch. I could have appended like something else. Some people do like a date, you know, that kind of thing. You can do that if you'd like. But I just appended the epoch. That's good enough for me. That creates new path. I am printing new path just so that I can find it later. But this is really the operation that does the heavy lifting. Torch.save. And what do you save? The model, right? And then where do you save it? New path. And new path will contain the name of the checkpoint and it'll save it to Scratch. So that way it creates these CNN model. You can see CIFAR-10 and then it's appending 0, 10, 15, 20, 25, which is the epoch that I'm printing at or saving it. Any questions on that idea? Yep.
So would you save that, like say, for example, you're running the training model, you're training the model, and then you notice your GPU is running out of time. Would you like save it right before then, or like how would you?
I would just let it, maybe it'll get to the one more checkpoint, or if you kill the program, just grab one of the old ones. That's the whole point, that it saved the model when it was stable on the hard drive. And now it's moved on. So you can always go back to one of those files that was stable and keep training from there or do inference from there.
What you can do also is after like having the code, after a certain amount of iterations, automatically save it. So that way it's like almost like auto saving, basically.
But that's what I'm doing.
Oh, my bad. Yeah.
That's what I'm doing, right? If you look over here, as the model, this is the training loop. So every 5 epochs, I save a checkpoint. Yeah, no, that's literally what I'm doing. Makes sense? Now I did provide, there's a lot more to this. Like you can save the classes, you can save optimizers, you can save lots of things. So if you guys, are in, like to like learn things like that, I provided this link, okay?
Like pickle?
This is Pickle.
Oh, it is.
The one what we're using is Pickle, which may be insecure, but this is a class now, so I'm not worried about security. All right, but there are other options, yeah. But this is Pickle for sure, which is the Pickle library from Python.
Also funny.
Yeah. All right. So does that make sense, guys? So that's the train loop, right? And that should save your checkpoints like that. So this definitely, I think, comes in handy because you don't want to spend 2 hours and then lose everything or something. All right. So once you've done that, this was the same. I just changed the number of epochs to 15 currently because I've been like debugging this. So I wanted to, I've noticed that after 15, it actually gets to 0.05. So that's like a good loss compared to the start at 1.3 or something. So I've been just running it quickly. You can see that the difference is the model is instantiated with the CNN net now instead of DL or MLP. So hopefully that should be pretty straightforward. Atom and cross entropy, those do not change because it's still a classification problem. And you can see what I've been doing, like printing 98, 55, 0.53. So these are the losses. And I print the name of the checkpoint, the last checkpoint. So I can, for ease of reference, find it. Questions? Nope. All right. And then after that, print metrics hasn't changed. Torch no grad. This is on the test set. This is the performance metric that I'm getting 0.19 at that point. If I ran 60 epochs or something, I might be getting something higher. This is higher than what we had it for the DL net. But some students have been telling me that when they run this exact same code on their GPUs, they get 40. So I assume this would give them like a 60 then. It's what I'm guessing right now on their GPU. Okay, got it? Right. So we're going to do one more thing today, but I want to show you this. Now, from checkpoint, right, you want to do inference. So what you do is I created a new variable called it model2 just to not confuse things. But basically, this is the function that should do the heavy lifting. Torch.load, provide the checkpoint that you want to use. Okay. And then repeat the same process. Remember, this has to, I didn't say this, but in the test set, you also comment out this line that we had before. Why? Because before we had to spaghettify it when it was a deep learning. But now if it's CNN, we use the hypercube. So it's a cube. Okay? So that's why you just comment out this line, like in the training. Exactly like that. And here you can see then you basically run model 2, and then here you predict with model 2 instead of the original model. So effectively, you should be testing from the checkpoint and not from the one in RAM, basically. Any questions? And that's it. This is the whole code. I need to add something today that I'll talk about. One thing that I haven't done that I'm hoping is the problem. And this was just something we were doing, printing out shapes, and I've already discussed what this is. That's it. This is the code that I will give you guys by tonight, probably. Okay, for you to play with. You can see that mine is getting 19, but that's a bug, I'm sure. Some of your classmates are getting 40. This would probably get 60. So we need to figure out what's going on the Scholar. Yeah, Henry.
Is that the average F measure, or is that the?
That's the total, just one of 10,000. 10,000. But when you run it consistently, it's always 18.9, 19.3. It's always very.
So that's just a random F measure out of the test set, one of the test set.
It's all 10,000. You can see if you look at these numbers, there's 10,000 in there. There's a 709, 690, 590. Those are close to 1,000. So there's 10,000 in there.
Okay, I guess I might not. I might talk to you afterwards about it.
There's 10,000 samples there, and the test set is 10,000. So this is out of all those 10,000. That's the F measure.
Right. I don't know. Okay, I'll talk to you later about this.
Okay. Yeah. Got it? Any questions? No? All right. So there's one thing that I need to add to this that I always forget. Okay. And I'm hoping this is the issue. So usually I use a lot of like libraries like transformers, fast AI, or things like that. Those libraries are wrappers around PyTorch. So they do a lot of things for you, like handling, connecting the data and the models to the GPU. Right. So I always forget about that. And then all semester, we've been using PyTorch on CPU, really, right? On the local machine. So there was no need to tie to the GPU itself. But generally speaking, you should tie certain things of your code to the GPU unit. Do you guys see what I'm saying? So that's what I'm going to show you today. I haven't tested this out actually. So we're going to kind of do it live, if you will. But it's something that we should do. And I'm using another script that I know has worked before. So I'll show you basically. So the best explanation, this is kind of a weird thing. It's like not exactly so intuitive, but you basically have to like grab your data and put it in the GPU. And you have to grab your model and put it in the GPU so that it definitely runs on the GPU. In fact, if you guys had multiple GPUs, sometimes you can grab parts of the model and put them in one GPU and another one in another GPU, and then they run in parallel and the model runs faster. That's why it's like this. It's like, all right, so we're going to go ahead and try to do that. So I'm going to go all the way to the top again to illustrate this, okay, this idea. And it's just another thing for you guys to try out. So we know that this works, right? So let me actually clear the kernel. So I'm going to start fresh. I'm going to clear it again. All right. So let's go ahead and run this one. Run that and that one. So I think let's do this actually. Let's check that we have GPUs. So we do. It's device 0, and it's an NVIDIA A30, which it seems to be what we always get. All right, so now in here, I'm going to add a new section. And I'm going to call it assigned device. Okay, assigned device. Markdown. Right, so we run that. So basically, we are going to create a variable that is going to hold whether we want to use the CPU or the GPU. Okay. So the way that this is usually done, there's like an if statement, but we know we have a GPU here. So it's something like if torch dot CUDA dot is available, which I think is one of the commands we had at the top. So basically it's a Boolean, just returns true or false. So if is available, then torch device, which is a variable we're going to have now. Some people just use device, I think. So torch device equal torch device CUDA. Does that make sense? So this is basically, this variable now holds whether we're using CUDA or a CPU. So for instance, you could do an else or simply just say torch device equal torch dot device CPU. And that's a convention, right? So you start with CPU, but if you have a GPU available, which is CUDA, then you change it to that device, okay? And this is going to be so that we can say sometimes to the code, hey, run this model on the GPU, run this data on the GPU. Okay, so that's the idea. Any questions about that? Okay, so so now we can print it also. So I'm just gonna say torch device. Okay, so let's run it. And it says type CUDA because it is available. All right, so that's what we're gonna be using. Okay, so we read in our okay. So let's run the rest. So this should be fine. Let we read in the data. That's the checkpoint library path. Load the train set from that takes a little bit. All going. Okay, finished. So now let's we're going to check the labels. You can save the data set. This is something we just did kind of just to show how it works. You're just doing some checks. I always like to check that everything looks like there are no errors, especially because we have a bug, right? So what is it? Okay, so we're doing this. Got the image. It's cat, so we're able to get images. We print the histogram. We've got, I can see 10 classes and 5,000 each, so there's data. We repeat the process for the test set. Print the shapes, print the histogram. 10 classes, 1,000 each. Balanced data set, which is good. Like I said, I did this part. I do always do this, make sure it's float 32. This is called sometimes sparsity as a big name. And it's basically, you can make models that are float 32, float 16, 8 bits, etc. And it's just a thing of, maybe you'll lose some performance and accuracy, but it makes the model way smaller. So maybe it can run on a mobile phone or Raspberry Pi or something. Henry, do you have a question? Okay, great. All right, so I did this part here. As I said, all I'm doing is I'm taking the torch tensors, converting them to NumPy, changing the data type to float 32 in case they were float 64 and that was an issue, and then changing them back to torch. Notice that I only did that for the X data since the Y data should be integers anyway. Okay, so I'm going to repeat this process. We can print the shapes just to double check. Everything looks good. You can see when you do item, you get an integer. So, I guess I could say type here, suppose. It's int. So it is int. So yeah. Okay. All right, so let's keep going. So these are mainly just checks. Remember, we create these lists of the data, and then we create data loaders from it. And we've already discussed that. We run the architecture, which is this one, the CNN-net. I already discussed that one. I already told you where 1152 comes from. We're ignoring the other neural nets. And then here, I'm just doing 15 epochs for now, so that it runs a little bit faster so I can debug. Okay? All right, so now comes another step where you have to do something. Okay? So here, I'm going to run this one. I could also change the learning rate to 0.03 maybe. Okay, so I guess I'll do that. All right, so here, the model. The model, we instantiate it, but we have to assign it to the GPU. So that's what I'm going to do here, okay? So how do I do that? It's called model dot to torch device. Do you see that, guys? So basically, it's putting the model in the GPU, if you want to think of it. Yeah.
And you also, I think you also want to do the same with data points, right?
That's what I'm going to do. Yes, I am going to do that. I'm about to.
And for parallelizing, once you do this, cast the device, you're like 90% there. There's just like a class you have to wrap around and all your functions. You basically can parallelize it too.
Yeah, I mean, that would be great if we had a multiple GPU.
When we send you the code that I use?
Yeah, send me that. I need to replicate that. All right, so did you guys understand this part? So I am tying the model to the torch device, and I also need to do the same for the data set, okay? So we've got that right there. That should all be the same. Okay, see it's doing things. Give it a minute. Okay, it finished. So before I run this training loop, I need to go, because the model is passed right to the function, but the data is extracted here from the training loop. Okay, so I need to do something here. Okay, so basically in theory, it would be, I think for the simplicity's sake, I'm just gonna do xb equal xb dot 2. Do you see that? And tie it to the torch device, which would be the GPU. So torch device. And I repeat that for the YB dot 2. And I'm going to tie it to the torch device. Okay? Does that make sense, guys? So you'll see this a lot in PyTorch code when you're using a GPU. All right, yeah, so I guess
May also
yeah.
wide print to be cast to the device. I mean, try to see if it works, but that may be an issue.
Well, YPRED, when it comes out, is tied to the device because the data and the model are in the device. So if anything, we have to, if we want to use it, take it out of the device. YPRED is coming out.
Because if you look at the loss function,
See YPRED.
setting YPRED and YB. YB is in the GPU, YPRED is in the CPU.
Is it? But it's coming from the model and XB, who are both.
Maybe. I would
Yeah.
run.
But you see my point, like, yeah, it's coming out of the GPU, so it should still be in the GPUs. But yeah, that's a good observation. Let me think about that one.
You can just run it and see if it works.
Yeah. No, I agree with you.
But I think that was the issue I had with mine when I tried to.
Hmm. And let me see that actually. All right. Let's try it like this. Okay. So let's see what happens. Where were we? So I think we were. Yeah, so then we would, I haven't run it yet, but the modification has been done. This has been done. So we run this function. Then we've got the print metrics, which is the standard one. And then I just want to check this here. So there, that we need to cast to the device. Do you guys see that? So because it's the test set also. So that's one thing I don't want to forget here. Yeah. So here, remember that the model is in the GPU. So we're going to have to send X real to the GPU as well. Do you guys see that? So that should be X real equal X real dot to torch device. Okay. All right. And then that's going to give us some outputs. And the preds will need to be sent to the CPU this time around. Okay, so that would probably be print metrics preds dot CPU. Because this is definitely a CPU operation. Do you guys see what I'm doing? Like, does the logic make sense? So you'll have to figure this out, but I'm hoping that this is all that you need to do. Okay. All right. So let's go ahead and run it and see if it gives us any. And then if we have anything else, we'll continue. But at this point, we should be able to run it. So I'm going to hit run here, training loop, or run.
I think .cpu, the .cpu function is the same as creating a device of CPU as like the first CPU. I think the .CUDA is the same thing, but with the first GPU.
Okay.
I think.
Well, we'll see. I mean, I know this has worked before, but you know, let's just see what happens. Okay. All right. So it's not giving us an error. That's good. This should run in a little bit. That's why I only did 15. The loss is pretty bad right now at 2.38. Everyone with me?
You can do it. I
You believe in me. Yeah. Well, these are the challenges with doing these things. You bring in GPUs. You guys have to learn how to code differently, right? In parallel, deal with tensors, and also deal with GPU. Hey, that's actually faster a little bit, but the loss is bad. Faster. 233, still pretty bad. So, but it's running fast for sure. So I'm gonna change the number of epochs to 60 and give it more time.
What was it at currently?
I did 15 because this would take me a little bit when I was trying it in my office.
So beforehand, we're just using the CPU.
Yeah, basically. And so now, it's obviously faster, right?
Yeah. Yeah.
So you guys that have your 490s and everything, you can definitely, oh, it finished actually. So let's look at the performance. Let's just actually test the code. So it's terrible, like literally terrible. Good. Huh? Okay, yeah. So this is pretty bad. Let's definitely, but it didn't break, right? it tied it to the GPU, which you need to do. So progress. All right, so let's go ahead and increase this to 60, right? So definitely we can give it more epochs now. So I'm going to go ahead and run this one. Okay. And then I just want to see this get to like 30 or something. And then maybe architecture of the CNN. Any questions, guys, while it's doing this? Do you guys have anything? Any suggestions? Huh?
We have questions.
You have questions? So besides Henry, that I know where he's at on the project, how about the rest of you? Where are you on the project? Like, what's your score?
The math score is like really low. It's like 0.8, but my loss is like 0.
Okay, so he gets to a pretty good loss, but the model's still not predicting well.
That'd be like overfitting the data set or something.
Maybe, yeah, but it's weird. So it's
where you're like overtraining the data set to where like it's like less generalizable, I think. Where like it's like learns the data set super well, but like you doesn't expand the test set. That makes sense. Like an extreme example would be like a function that just loops the data set, finds the exact same vectors and outputs the label for that. Right, that doesn't generalize at all because like once you that would be an example of extreme overfitting. So like a way to avoid that would probably be to like less epochs or something.
It's because I started at like 100 and I went down to like 20 and then 10.
Oh,
it's still very low.
Then it probably is the architecture. I don't know.
so okay, so it's 2.21 now. How about you, Quentin? You seem to be smiling like, huh?
I'm good.
You're good? What's your score currently? Very good. With this, right? With PyTorch?
Yeah.
And you did a CNN architecture? Okay. You're not using some library, right? Like FastAI? And more CNN convolutions, possibly?
Yeah, it takes a while.
Yeah. And you use residuals? No? Okay. Okay. But did you use other tools like Dropout and yeah. I'm gonna show the class that today. So I'm gonna make these changes. So I'm happy that it's not giving me an error. I do believe it's on the GPU.
Can you use transfer learning?
You can only if it's from Torch itself. Like Torch Vision has a ResNet. If you can figure out how to use the ResNet from Torch Vision in your CNN, yeah.
Or is my homebrew good?
Homebrew is for Mac, but I just mean Torch Vision.
I mean like my homebrew.
Oh, what you created? Yeah, of course, absolutely. Okay. Absolutely. So I'm noticing that this loss is not going down. Do you guys see that? Yeah, it's not going down. So what do we do? So I'm gonna just throw a lot of things at it. Learning rates. But I'm gonna do like a very basic thing. Yeah, because that learning rate just does not get better. I did 60, right? Yeah, so it's gonna be done soon. So let's just see if there's a slight improvement. Well, actually, while it's doing that, let's start changing that architecture. So the things that I'm going to add is I'm gonna change ReLU to leaky ReLU. I'm gonna do leaky ReLU instead of ReLU. And I'm gonna do a dropout also after the max pool. And dropout, I think I had described this already, right? Is where like some connections get disconnected, basically. All right, so I'm gonna do nn dot drop out. And I'm going to drop with a rate of 0.2, 20%. Yeah, you don't want to drop all the connections, so it's about 20%.
But you don't specify anything else.
Is it? Okay, great. All right, so I'm going to add
a lot of time actually.
Yeah, I'm adding a comma there. All right, and I'm going to repeat that technique here as well, leaky relu. So as I said, this is what people do. They use all these constructs. As I said, if you make it very deep, but there's also something called batch normalization. I may be adding that as well. Normalization, I've said this, right? Helps out a lot. So we want to consider that one. But I'm going to add a dropout here. But I don't want to make this more than 2 convolutional layers, right? So that part I'm going to leave to you guys to figure out. All right, so I've done that. Let's see if it finished. Yeah, it did finish. Yeah, and that didn't change at all. So yeah, it's still pretty bad. So it's actually worse than before. So I'm gonna add this new I want to find batch normalization. So it would be something like this. Here, probably maybe after this one, nn dot batch norm 2D. 2D, and then you have to specify here a value. So I think it's 16 for this, if I remember correctly. Okay, but basically you're trying to normalize these values. And this would be 32, because that's what's coming out intuitively. All right, let's try this one again. So it's a new architecture. All right. Any questions?
I'm so good with this contest. That's my goal.
That's really great. It's really great.
Oh, and a very stupid question.
Mm-hmm.
The batch size. That seems to affect the training, right?
Yeah, you can keep it at usually 16, 32, 64. People don't make it bigger than that in general. You don't want to give, because it's batch normalization, right? It's only normalizing over the batches. It's learning over the batches.
Right. And you don't want to be too small, right?
I mean, 16, I think 32 is a good number, actually. That's something. I mean, we could change the batch size to something else.
I had mine 128.
Yeah, I mean, you can try that. Guys, any questions? Is this making sense? So it's not erroring out. But it's not learning. Resetting.
What was that one measure again?
That's quite low. All right, so it's still training, not improving at all. Did you have this for a long time and then it started to improve?
It started off at 0.09, right at one. And then I'm at over 0.6.
But a long time to train?
Yeah, it takes a while. I'm not doing CPU, but I'm gonna switch to the GPU.
Oh, you're still doing CPU?
Yeah.
Okay, so hopefully this code
I think
should run.
like I think that one of the issues too could be is you're not averaging all of the F1 measures, right?
I'm just doing one. So everyone is supposed to do one. But run the Jupyter 10 times. You know what I mean? That's what when I mean, yeah, I know you're confused. So Henry, look, when we look at the histogram of the test set, right? There's only 10,000 samples there.
Right.
1,000 for each of the 10 classes. So you are going to give a batch of 10,000 to the model, inputs, images, and the model is going to predict 10,000 labels. Then you compare those with the real ones and get the F measure for that. And everyone's going to do the same.
Okay.
When I say repeat it 10 times, I just mean run the Jupyter 10 times, but you're not changing the code. And the point is that you look at those 10 times, and sometimes it was 0.80, something. Yeah, exactly. But in general, that's what you're doing. Yes, sir.
Now, do you want us to run it 10 times, or do you recommend us to run it 10 times without changing anything?
You shouldn't change anything. So the test set code should not change. What I mean is just run the Jupyter 10 times.
I guess I'm.
Just be consistent, just be convinced that you didn't just like randomly somehow get a 97 on a Wednesday night, and you're going to come here and say, well, you know, that Saturday morning at 3 a.m. I got that 97, but now I can't get it. And I should win because of that 97, because this every year there's one student like that. And you know what I mean? So you need to kind of consistently tell me your values so that you can show, because you can grab the checkpoint and do the inference, right? And that's not going to take.
Can you show the testing loop really quick?
The what?
The testing loop?
Yeah. Yeah, actually, the model just finished running, right? So, see, the learning rate is terrible, but I'm only doing 60. It's possible that I need to do more, right? More than 100. All right, I'm trying to make this easier for you guys by throwing a lot of things at it, but I even threw batch normalization. Yeah, I'm going to do that now. So it finished training. So then you run, and then here you run the test set. I mean, it's a little bit better. It's not all zeros. Do you see what I'm saying? The code is running. I do believe it's running faster for sure, because I would still be on the first try if I was running this on the CPU.
I guess I'm confused with the loop, because it seems like
You're confused with the loop? What loop? There's no loop here.
4 X real, Y real, you're getting.
It's just once, just one time. Yeah, it's that loop only runs once. It's a terrible code. I know. I'm a terrible programmer.
Oh,
but that's what it is. It just runs one time.
Yeah.
Why?
I'm joking.
Yeah.
No.
Because the batch size is 1,000.
Okay, so average.
But sometimes I may want to do it in batches. And so that's why I always do it like this.
Okay, so averaging it wouldn't do anything because the count's always going to be.
Yeah, if you look over here, look.
My bad. I was misunderstanding.
This will clear everything for you. Take a look at here. The data loader. This is the key. Here, the batch size is 16, right? What is the batch size for the test set?
Probably one. Yeah, one.
No, 6. It's right there. 10,000.
I'm sorry. The iteration is going to be
1.
Not 10. Yeah, the iteration is going to be
Iteration 1 because the batch size there's 10,000, and I'm saying grab 10,000. So in the first iteration, it grabs 10,000, and the second, there's nothing to grab. It's done.
And if you were to change the batch size to like, I don't know, 32 or something, you would then want to average out.
Yes, but I don't want you to do that.
You don't want me to do that.
No, because then you change a little bit.
Okay, that makes sense. Yeah,
it may be okay, but I just want everyone to be consistent, right? What if he gets, 85 and you get 86, but you have that little change that could give you the edge?
I feel so stupid.
No, it's all right. I mean, I should have done it better, but it's just, I like it that way.
Language that's called, not you.
I kind of like it that way.
Yeah. You bring pattern matching to Python. Okay.
Yeah, I just kind of like it like this, it's just pretty standard,
Right.
So anyway, the model, in my opinion, is better than before. So definitely we should train it for longer. Yeah. And you guys are free to go out and find other constructs as I was doing, right? So I kind of showed you like what I was doing. I changed this to leaky relu. What if you change this to Jelu? I definitely recommend the batch normalization.
I think might support if you go to test function.
Yeah, I'm listening.
And, if it's not a list, right? It's It's a tuple, right?
What is?
The
data loader?
The data loader.
The data loader is a torch construct. So it's got its own thing. It takes a list for sure, but it's going to convert it to a serialized. Remember, everything is serialized for speed. So even the data loader is no longer a Python.
Can you go to the test function?
Yeah.
This is just test. It probably won't work. But see if you can. Oh wait, where's the?
The what?
I'm sorry, I thought it was a function.
It's not a function.
Okay,
With Torch no grad just tells it not to train the model.
Go up then I guess to where TestDL is.
So where's what?
Where TestDL is.
TestDL is the data loader. It's the
Rather than
torch.
having like a list, could you like have it like we have tuple or something? Like instead of train DL.
Yeah, but then you're talking about not using a data loader and just using your own thing, which you could. This is how it used to be done.
No, for the test set,
I mean, but then you're changing the fixed things of the challenge.
Okay. My bad.
Yes.
But it's going to be the same thing, right? Because it's going to be one iteration because you're repeating it back.
It's one iteration, yeah.
Right.
So
it wouldn't matter if you just pattern match like the first element of that. Or not the first element, just like replace TestDL with like a tuple, right? Of like A and B or something. And just use A and B directly. That we don't have to use the for loop to.
yeah,
Probably,
yeah, but why?
Well, maybe more elegant or something.
Yeah, you want the code to be more elegant.
I don't know. I mean, no. It's fine. I'm sorry.
No. This is standard procedure. Like,
right. Okay.
Everybody uses train data loaders because
Right.
they minimize. Otherwise you have to do 10 lines of code to do the same thing.
Okay. I was just thinking of a way to like abstract away that for loop. Then only goes one iteration.
I mean, Henry.
Sorry.
Well, one reason why I may do this is what if I had 1,000,000 samples? Then at that point, I may get a memory error.
That's true.
And so an easy thing is just go to the data loader for test, change that batch from 1,000,000 to every 60,000, and then we do what you want to do.
And then at that point you have to average the S measure.
Yes,
okay.
Exactly.
Yeah.
But see, my code works in both scenarios with minimal change.
Right.
And that's nice.
Sorry.
Yeah. That's all right. So yeah, I don't know if you guys have like any ideas of what we could add here. You could add 2 more flatten layers here. More convolutions. Do you guys want to add a third convolution and see what happens? You're laughing. You think that's gonna... Oh, is that a crazy idea? Huh? It's pretty fast right now. But you guys, what I'm showing you right now is what I hope you will all go do, right? Play with this and understand that this is what people do to create good models, right? All right, so convolution 3. So I added a third one. So now what comes out here is 32. Therefore, this needs to be 32. And I'm going to leave it at 32, 32, 2. But see, this is going to change, right? Maybe. So we got to redo that part. So how do I do that? I need to copy this whole thing again. I'm going to scroll all the way down. Model C equal. Just going to comment this one out. Okay, maybe it won't, but I like to check because I don't want to, I want to know what to expect. So here I have a third convolution and a flatten operation. So then I just need to add this one and then, oops, sorry, that one. And then it should work, hopefully. So let's take a look at if the dimension has changed at all. Oh, so it should just, oh, there. That, okay. 128. It's smaller, which makes sense. It's funneling, right? So what is the impact of that? Let's try it. Do you guys see what I'm doing? A third convolution, funneling it came out smaller, right? Unless I've made a mistake somewhere, but it didn't error out. So you gotta change these things. There's more things you can add for sure. Let's go to the network then. What was it, 128? Yeah, 128. So let's go to the model. CNN. This would need to be 128. Got it? All right. Okay. Try it. Huh. $209. It's a better loss to start with. Did you? Yeah, go ahead.
So how come? But then they changed the 512 after. Aren't they supposed to?
Not really, because it's like this. That's a good question, right? So I don't have my stencil, so it's on the board. I do have markers. That's a good question, right? So when we create an architecture, we do this, right? So then if this is, let's say 60, and then this is 40, in the thing, we say 60 and 40, right? But with the CNN, what you're getting is you're getting a cube, a hypercube that comes out. And we need to flatten it. So that's another operation. So it basically just makes a copy of this, but spaghettifies it into whatever it is. Right? And so that literally is what needs to go to the other connection. So the 512 is this one. But this one, we don't know because it's this one. And this would not connect to this one. By flattening it, now we know this is 128. Therefore, that's 128, but the other one just is 512 because it's basically another layer. Yeah, you have the 512. Yeah, you could make it whatever you want. 4096. It's another layer. Yeah.
And a hypercube is just like an object of like d dimensions.
It's a tensor, yeah.
So like a cube would be hypercube of 3, a plane would be hypercube of 2.
So that what?
Like
Say that again. Sorry.
like a cube would be a hypercube of 3.
Yeah, cube. A normal cube is a size. Yeah, exactly. A cube is size 3. Hypercube is just a term for more than 3.
Okay.
Okay. Yeah.
So it isn't just a d-dimensional object. It has to be at least
Greater than 3. Yeah. Yeah. Hypercube. Yes. Hyperspace, hyperplane. It's the generic term used to denote things of R greater than R3.
Stupid question. Is a hyperplane just exactly one dimension less, or can it be less dimension?
A plane is a plane, and then a hyperplane would be in a higher dimension, like 1 dimension more or above.
Okay.
So wherever the definition of plane falls in whatever space, probably 3-dimensional space, right? It's cuts it. So
like a
hyperplane is a plane in 4-dimensional space, cutting it somehow.
Okay.
But we can't visualize it because we can't see like that.
Right.
Hey, the learning rate is improved. The loss is improving. 1.9. Yeah, Aiden, please.
Is the loss kind of linear to the F1 measure? So kind of you can envision what you're up to?
Yes, exactly. One thing I always like, when we were getting only 2s in losses, I felt bad because I knew this is not a good model. What I want to see is this loss go from 2 to 0.003. If I see that, I'm going to be optimistic. Now, of course, you still need to look at the test set, but I would be hopeful. Yes, sir.
Should we funnel that 512 to a smaller value?
Maybe. I can't tell you. I mean, sometimes you make it bigger, sometimes you make it smaller. There is an optimal way for this specific problem, but yeah,
win that contest.
Good.
That's
Play with it.
I like that trophy.
It went up again. That's up.
But to be fair, that's just like at that specific epoch, right?
After 28 epochs, yeah. It's not converging quickly, I can tell you that. It's at least taking its time. So you have to run, one time run my code for just the whole 2 hours or an hour and a half, whatever that would be. You can time it. You take a clock right now at 25 and hit timer. And then when it hits 25, stop it. And then you can tell how long it'll take to run. And then just give it like an hour and 40 minutes of that. And see where you're at. Yeah.
If you're on the GPU and you're training your model and then you run out of time, will the model stop? The code will break or no?
The code will break, but that's why I've given you the checkpoint. Yeah. So if that happens, remember you are saving checkpoints. You can see here the time you can see is changing, right? And these are the checkpoints that I'm creating. So you can just reference back to maybe it's a good idea to put the date and time in the name so that you can actually know, which checkpoint you want to go and retrieve. Got it? Any other questions, guys? Yeah, Henry.
If you accidentally delete your files or something, I think every midnight Eastern, Slurm keeps a CFS snapshot of your entire home directory. So if you want to recover your files, I forgot the exact command or whatnot, but if you know how to handle CFS snapshots, you can just do it directly that way.
So this has a CNN with 3 convolutions. You can change this to leaky relu. You can put dropouts here. Actually, that might help. Don't put anything after softmax. Basically that one. You guys get the idea? Just 1.897. So I don't think we've ever reached 1.897 so far tonight. Maybe.
I think you're looking for a general trend, right?
I would like to see something, yeah, because I don't like seeing it go back to 2, for instance.
Right, but that's over like 5.
It currently is 40 epochs. 40 epochs. So remember, every one of these 40 epochs, I've given it the whole training set to look at. All right, guys, the last thing I want to show, let's leave it training. The last thing I want to show you is for the final project, you need to build basically a very simple neural net and deploy it on GitHub using Onyx, right? So I provided a code example of this one. Should be pretty straightforward. And I'm going to point it out right now. So that should be. So all the code is there. I think this is way simpler than the KNN one. So let's take a look. So let's go to GitHub here. Should be under your course. Homeworks. So the where did I? Oh, deploy to web pro. There it is. So I added this, okay? Make a mental note of where this is located. Machine Learning Foundations, deploy to web. You had seen these examples before, but I have provided basically this for you to kind of replicate for your project. You do have to use another data set, but keep it simple, right? Use some kind of simple data set. I'm not looking for really a lot of great machine learning here. That's CIFAR-10 is for that. This is just so that you learn that you can deploy your models with Onyx to the web. Yes, Henry.
Can we use a machine learning model that just like has that just randomizes the weights?
Well, I mean, you want to predict something. So in this example, what did I do? I provided the wine quality data set. I don't know if we ever did that one in class, but it's a CSV basically. And you look at acidity, alcohol level, etc. of wines, and then it gives it a rating like 1 to 10, something like that. You see that? That's basically the machine learning algorithm that can be used for classification or regression, either way. But this is just an example, okay? So basically, the CSV data should be here. So if you click on that one, it takes you to here, and you can see the data set is right there, wine quality CSV. Does that make sense? So as you can see, it's just a simple CSV. My suggestion, get one of these. Don't use, obviously, the wine quality, just some data set. Okay?
Should we use the iris?
Not iris either. Just find something, right? So I'm trying to keep this simple, but I don't want you to miss knowing how to deploy something from PyTorch to the web, like your own app with Onyx. Because you can actually deploy even chatbots and things with Onyx. It's very powerful. It's actually one of the most powerful things currently. So anyway, so I provided so my suggestion, replicate this, okay? First. So the CSV is here. And then, so we can, that's basically the link. So go back. And then here, you can go to this link. And everything that you need is here. The Jupyter is here. And then the website is here. So what do I mean by that? NN, if you look, is what's deployed on GitHub, right? So it's got the index HTML, the index.js, and what is that? Onyx. Do you see the extension? .onyx. So the model that you train gets exported into this file. And then the index and JS bring that in for inference. Got it? All right, so let's look at the Jupyter first. Yeah, Jupyter. So the Jupyter is this one. Notice it's called regression, NN, and XGBoost, PyTorch, because I have actually two algorithms in there. But forget about the XGBoost one. Just focus on the NN one. So you deploy a neural network. So you can click on this Jupyter. And basically by now, I'll just describe it so you can see it's got the libraries, right? And the new libraries are, of course, Onyx Runtime, Onyx Tools, and so on. These are the Onyx libraries that will allow you to export, okay? Or import also, because you could actually import an Onyx model into Python and run it from there. Some of these are just for the wine quality to create a machine learning model. So you can see it's got batch size, learning rate, all that stuff. It reads in the data from CSV, and then it loads it into pandas. So again, find some data set with like 6 or so features, and it predicts some classes or regression values. So here it just goes into that, the correlation matrix that we have looked at before, and then the process of converting the pandas into NumPy, and then Torch. Give me a second. Torch. Notice the thing where I fixed the float 32 error, normalization, just like before. Once again, data loaders, right? You create your data loaders. And then here's a very simple set of neural network architectures, like an MLP and a DLNet. Okay, so all of this is exactly what you guys have done before. Train loop, hopefully no surprises, is the exact same thing. Notice, though, that model is the instantiation of a DLNet, and this is the thing that you need to export to Onyx, okay? So do some training. You can evaluate the performance. Similar to what we've done before, I printed all of this. Scroll all the way down. And somewhere, yeah, and then here, believe it or not, that's it. Okay, so if it says XGBoost, just ignore the rest of the code. So what do you have to do? This is how you export your model into an Onyx file. Notice that you put it in evaluation mode, and then you create this tensor is a dummy tensor that means the input. So in this case, we had 11 features for this model. So that's why it's 1 by 11, because it's the batch size of 1 by 11. Do you guys see that? And then basically just define this exactly as is, and you invoke torch.onyx.export, and you provide to it model, the dummy input, the name of the file, and then just leave this as is, and you're done. Your model is now exported to Onyx as one single file. Keep in mind, though, it probably needs to be less than 25 megabytes for it to run on GitHub. That's it. Yeah.
And we have our own website. We don't have this restriction. So.
Of course, like if you were deploying your own GPT, export it to Onyx, and then whatever, it was 1 gig or whatever, run it from your, exactly. But since most of you, I think, will be using GitHub, you do that, have that 25 megabyte limit. All right, so now that we have like 7 minutes. So now that you have this Onyx model, what do? You need to load it to your HTML and JavaScript, similar to the KNN project, but this does not use PyScript. So this is only pure JavaScript. And you guys know how to use JavaScript. So let's go back. So now notice, this is the Jupyter, okay? And just go to this one, NN, and basically you just upload the Onyx, and then you have 2 files. The index is pure HTML. So notice you do have to import 2 script ones. One is for Onyx, right? You can see Onyx min.js. And the other one is for your code, the index.js code that will handle Onyx and do the inference, okay? This is the table because the CSS, actually, the CSS. And then basically this code is very simple. In the body, I have 11 inputs, which are text boxes, values, right? And then you have a button that calls run example. And then basically here, the predictions are going to be sent to this div by ID. That's it. That's the whole HTML, okay? So now really the trick is, let's take a look at the JS file. And that's it. So you create the function run example in JavaScript, okay? You need to create a variable of the size 1, 11 for this example. Why 11 again? 11 features, right? That's the input to the model, right? Create this var x, and then what is document get element by ID? It's just an HTML thing to extract the values that you enter into the 11 text boxes. You guys see that? You collect all that data into X, and now you need to convert that into a TensorX object for Onyx. All right, so basically you're going to do new Onyx.tensor, you give it X, you tell it to be float 32, you specify the dimensions, and that's it. And then comes the object called for the session with Onyx. So you need to load the model. So you do new Onyx.inference session, you call it session, and then notice you do session load model, and you load the Onyx model. That's it. And then what do you do after that? Session run with TensorX. And what is that doing? Taking the input from your text boxes, throwing it into the model to do a prediction. That's it. Nothing more. And after that, the data is an output map. So you just extract it, and the rest here is just JavaScript for writing that value into the div tab. I mean, this is just like dealing with precision, so it doesn't show too many zeros after or too many numbers after the period. But that's it. So that's everything that you need. So this HTML, a CSS, JavaScript, HTML, and you need the Jupyter to generate the Onyx model. Okay, so for this project, as I said, find a simple data set. Yeah.
And we have to use Onyx, we can't just use Bonsai or something.
Yeah, you have to, yes, exactly. You have to use Onyx. All right. So that's it. If you want to look at other examples, I provided a few more, but this is the simplest one, I think, and the one that has the Jupyter, but the other ones can also help you. We got 3 minutes. So if you go to deploy to web, I provided all of these. So these two at the bottom are you should be familiar with them, are the PyScript ones. And then these 4 are the Onyx ones. So you can also look at them for ideas, because this one group did image classification. This is the wine quality one. Someone used a camera to capture the images that way, and so on. Got it? Any questions about that? All right, that's it. That's pretty much it, I think. Hopefully, yeah, it's not, I don't know. Okay, it's a little bit better. 0.15, 0.16. So I did 60 epochs. What's the logical thing to do? More epochs, right? More epochs.
Basically, you're trying to find the curve where you get the emission.
I want this loss, Henry, to go down to like 0.005. This loss value here should not be 2. I want it to be 0.05.
And what loss function? Oh, yeah. The
Cross entropy. We'll talk about that Tuesday.
Okay,
Tuesday. That's next week. I'm pretty much done, hopefully, with code for the semester. All we have left next week is pure cross entropy and things like that, unless you guys have questions. We're going to do, my plan is to do both the competition and the projects the last week before finals. Does that work? So you have this weekend, all of next week, and the following weekend. And I will load this code tonight. All right, but yeah, that's it. So as I said, next week is just pure theory. So I'm sure you will love that. All right, definitely see me during office hours, guys, if you're having issue. Okay, you need to remember Tuesdays and Thursdays, 2 to 3:30. I don't want you running around during finals week trying to find me to present your project, right? That's not ideal.
Why are you looking at me? It wasn't my fault.
No, all right, guys, have a good weekend. Have fun with the project. Yeah, give me a second.